Welcome to the module on the first law of thermodynamics. In this module, we will introduce the concept of internal energy and formulate the first law of thermodynamics. In thermodynamics, the first law is fundamentally about the conservation of energy. But what exactly do we mean by conservation of energy? The principle of conservation of energy is the idea that the total energy of an isolated system remains constant, being conserved over time. Within such a system, the energy can be neither created nor destroyed. While the total amount of energy remains conserved, energy is quite dynamic in nature. Energy can be transformed or transferred from one form to another, be it kinetic, potential, thermal, chemical, or any other type of energy, without appearing or disappearing spontaneously. This principle is not just limited to thermodynamics. It is universally applicable and is represented in various forms across different branches of physics. It is grounded in empirical evidence, being based on the outcomes of numerous experiments. While it has an empirical foundation, there is also a sophisticated theoretical proof that supports this principle. In our previous discussion on the general principle of conservation of energy, we talked about the total energy. As we apply it specifically in thermodynamics, our interest shifts to a specific form of energy known as internal energy. The name has it. As internal energy of a thermodynamic system, we understand the energy contained within it. It specifically excludes both the kinetic energy of motion of the system as a whole and the potential energy of position of the system as a whole with respect to its surroundings and external force fields. Imagine a propane canister inside an airplane. For an observer on the ground, this canister possesses kinetic energy as it moves with the airplane and potential energy because it is located high above the ground. But are these forms of energy that are relevant to the temperature or the chemical reactivity of propane? Not really. When we refer to the internal energy of a system, like a propane canister, we aren't focused on the energy it has due to its motion relative to an external observer. Instead, we are concentrating on the energy that is contained within the canister, meaning defined in a coordinate system that is fixed to the canister itself. Diving deeper, let's break down the constituents of this internal energy at a molecular level. Translational energy. This is the energy associated with the movement of molecules as a whole. Energy of molecular vibrations and rotations. Molecules can vibrate and rotate, and the energy of these movements also contributes to the internal energy. Energy stored in chemical bonds. The energy stored in chemical bonds is also part of the internal energy. It changes during chemical reactions. Intermolecular potential energy. This refers to the potential energy resulting from attractive or repulsive interactions between molecules. Potential energy of the molecules in an external field. Consider, for example, a substance made up of polarizable molecules. When an electric field is applied to it, the potential energy of these molecules changes. The total of all these forms of energy for the system of interest is what we term as the internal energy and denoted by the symbol U. The internal energy is an extensive property of a system that depends on the size of the system. These are the forms of energy that are relevant to our course. They are expected to change in physical and chemical processes that we consider. We could also consider other forms of energy, such as the binding energy of atomic nuclei. However, these energies do not change in the processes we study and thus are not relevant to our course. After we have formulated the concept of internal energy, we can apply the principle of conservation of energy to it and formulate the first law of thermodynamics initially for an isolated system. The primary assertion of this law is that in an isolated system, the internal energy remains constant. Now, you might be tempted to ask, is this just a simple, even silly statement? Essentially, we are saying something that doesn't interact with anything has something inside that does not change. While it might seem straightforward or even commonplace, it holds profound implications. This is the most fundamental formulation of the first law of thermodynamics. It asserts that the internal energy U is a state function, and as such, it possesses specific mathematical properties that are exploited in thermodynamics. The first law of thermodynamics expressed in this simple statement is actually a cornerstone in our understanding of energy and its transformations. How can we apply the first law of thermodynamics to a system that can exchange energy with its surroundings, a closed system? We consider the combination of a system and its surroundings as a globally isolated system. Then, the change of the system's internal energy, delta U, plus the change of the surroundings' internal energy, delta U sur, is equal to 0. Note that here and further a quantity without a subscript refers to the main system that we consider. It means that for a closed system, the change in its internal energy, delta U, is the negative of the change in the internal energy of the surroundings, delta U sur. How can we alter the internal energy of a system? All changes in a closed system whose internal composition doesn't change can be viewed only as heat transferred to or from the system, as work done on or by the system, or a combination of both. Therefore, for a closed system with an unchanging composition, the change in internal energy, delta U, can only be attributed to the flow of heat and work, or both, across the system boundary. The flow of heat and work, in turn, changes the internal energy of the surroundings and brings the overall energy into balance. This crucial insight leads to a second and more useful formulation of the first law of thermodynamics for a closed system with an unchanging composition. Delta U is equal to Q plus W. Here Q designates heat and W designates work. Let's look again at the first law of thermodynamics for a closed system. This law always applies to all possible changes in a system state. Because of this law applies even for infinitesimally small state changes. Although we derived it initially in the form of finite changes, such as state changes from 1 to 2, that are not infinitesimally small, we can also extend it to infinitesimally small state changes. This means we can write the first law of thermodynamics in differential form. du is equal to delta Q plus delta W. Now, let's look closely at it. The internal energy U is written with a small d, while heat Q and work W are written with a small delta. This equation already tells us that U is a state function and Q and W are path functions. And this is the best form of the equation that expresses the first law of thermodynamics. From a mathematical perspective, what is written here is miraculous. We have here two path functions whose values depend on the exact path between initial and final states. The sum of these two path functions gives a state function, whose value is independent on the path between two states. Purely mathematically, without observation of the natural world, no one could guarantee that such a phenomenon would occur. What is written here is not just mathematics anymore, it's a law of nature. And this law is, of course, the first law of thermodynamics. Here we would like to note another property of the internal energy. These equations tell us that the flow of heat and work between a system and its surroundings always leads to a change in the value of the internal energy. However, it is not possible to perform a thermodynamic process that would allow us to measure the absolute value of the internal energy. Nevertheless, you will see that it is not important. Now, let us briefly discuss the sign convention in the first law of thermodynamics. We use a thermodynamic convention in which work and heat are positive if energy is transferred to the system and negative if energy is lost from the system. In other words, the flow of energy as work or heat is viewed from the system's perspective. Therefore, we have the same sign for the change in internal energy and the changes in heat and work. With respect to heat, this convention also matches our everyday definition. When a system is heated, we say that heat flows into a system and not, for example, that a certain amount of cold is being removed from the system. With work, it's a bit more complicated. In thermodynamic convention, the work is positive when it is done on a system. The useful work performed by a system is thus negative. Sometimes you might see this equation with a minus sign before the differential of work. This representation implies that work is considered positive when the system performs work. This notation is more technical, suitable for engineering subjects, and should be avoided in our fundamental course.